Hello, hello, hello. Welcome everyone to our KDB AI vector database live stream. I'm your host, Neil Kanungo. I'm joined with Ryan Siegler, our data scientist, and Michael Ryboy, our new developer advocate. Michael and Ryan, you want to say hi?
Hey everyone, thanks for joining.
Hi guys, thanks a lot.
We're really excited for today's session. Whether you're joining from your morning, your evening, your afternoon, wherever you are around the world, we welcome you to our live stream today. We're going to be talking about hybrid search. And hybrid search is a great way to improve the accuracy of your search and your retrieval with your vector database. So there are certain advantages in KDB AI that are just released in KDB AI 1.1. You can try that out on our KDB AI Cloud or Server Edition. And we also have some other cool releases, some features in temporal similarity search, which we're going to cover in our next session. And we have a new integration with Llama Index, which is pretty robust, and highly recommend checking that out. So for today's session, I just wanted to start with a little bit about who we are and how you can get started. So let's get started with, some intro slides as people join, and then we'll get into the meat of the subject on hybrid search. So KDB AI is a vector database that's built on the KDB engine. It's a highly performant analytics database and analytical database, and we are priding ourselves on having very good performance, a very strong engine behind us, high scalability, and great for enterprise use cases. In addition, we are very strong in temporal and time series analysis. So if you're trying to do pattern matching with structured time series data, forecasting, anomaly detection, we're your go-to. So you can visit us at kdb.ai in your browser, and you can sign up at the top right. From there, you'll get two options. I recommend the KDB AI Cloud. It doesn't require you to download anything or deploy anything. You just get an API key and you can get going right with your Jupyter notebook or Python interface, whatever IDE of your choice. So that's a great way to get started for free. And as long as you're using the database, we won't cut you off. There is no time boxing on it. So you can keep using it in perpetuity. We get 4 gigabytes of memory for each instance and 30 gigabytes of storage. And if you want to expand past that, then I'd recommend trying the server edition and reaching out to us. And we can talk about your scalability needs if you want to put some more robust applications into production. When you sign up, you get a simple sign up form. If you fill that out, you'll get an email that you click the link for confirming your email address, and then you'll get another email showing you how to get started with KDB AI. When you join and sign in, you'll be presented with your API endpoints and your API keys. Make sure to copy those API keys, because once you get them, you can't access them again. You can delete them and manage up to 3 API keys if you want. But it's good to keep those API keys in your records so that you can always access your vector database instance. We have a new quick start guide in our user interface that will help you get going from scratch, how to set up your prereqs, how to create a table, load in vectors and embeddings, and select indexes. It's all right there for you. And we also have in our Learning Hub, I don't have a slide for this, but in our Learning Hub, we have 7 new articles that we just released last 2 weeks ago on multimodal RAG, temporal similarity search, hybrid search, metadata filtering, all kinds of cool stuff. So visit our Learning Hub on our website, and we're going to keep the articles coming through for you. Also want to mention our YouTube channel for those of you that are maybe having to hop off early or can't catch this live. All the recordings for these sessions are on our YouTube channel. So you go to KX Systems on YouTube and subscribe to us. And that's a great way to stay up to date with our latest content. And lastly, I just wanted to point out our Slack community. Once you sign up for KDB AI, you'll have access to our Slack community where you can ask questions. We got about 1,000 people in there. Good community, good way to expand your generative AI and vector database knowledge. So with that, I wanted to hand over to our feature session, and we will be joined. We are joined today with Ryan Sigler and Michael Ryaboy, and they're going to be talking about optimizing retrieval with hybrid search. So with that, let me go ahead and hand it over to you guys. And oh, sorry, one more thing. If anyone has any questions, be sure to just put your questions in the chat, and we will answer your questions live. We like to keep things interactive and fun, so the whole point of a live stream is that we can all participate together. So be sure to just put your questions in the chat, and we will answer those live for you. Ryan, you want to take us away?
Sounds good. Thanks for the introduction, Neil, and thanks everybody for joining. Today, we'll be diving into the topic of hybrid search and how we can use that to improve how accurate our vector databases are, and in turn, of course, improve retrieval for applications such as retrieval augmented generation. So with that, let's just get a quick agenda for the day. I like to start these presentations just with a quick overview of vector databases as a whole, what they are, what they're good for, and then we'll dive into hybrid search, have a nice high-level introduction, and then Michael's going to take it away and dive into some of the more technical aspects of hybrid search, how to build sparse and dense vectors, and how to actually do the different types of searches available within KDB AI, as well as a bit of hyperparameter tuning. And then we'll talk about some use cases, as well as how we can intertwine hybrid search into our retrieval augmented generation pipelines. And then after all that, we will dive into a coding demo, just demonstrating how we can actually implement this in practice. So let's go ahead and get into it. And I know Neil just talked about this a little bit, but KDB AI Cloud, super easy and fast way to get started. You could go sign up today and pull up our sample notebooks from our GitHub page, and you could get a hybrid search sample running in a matter of minutes. So check that out. All right, so let's start with just a sort of a baseline on vector databases. And what a vector database is, it's a database that holds vectors. And it's sort of obvious when you say it like that, but what can we actually use it for? And that's to take whatever kind of data that we have, whether it's text, could be music or audio, could be images or video, and we can store that in a vector embedding format or in vector format within a vector database. And when we do that, we can do certain things like find trends and anomalies and find similar vectors very efficiently and very quickly. So that's why it can be really a good way to take our data, do very fast and efficient processing on it, and then introduce that to other applications as well, like generative AI models and large language models. So how this works at sort of a higher architectural level is that we take our source data, whatever data that you're interested in, whether it's your private data, it could be enterprise data, and we take that and we run that through an embedding model. And what this does is it represents our data, our original data. It represents the meaning, as in the underlying semantic meaning of that data. And it does this because it is able to capture the relationships and the features, as well as keywords and the importance of all these things within a numerical format, which is a vector. And you can think of these vectors similar to like 2D or 3D vectors, just sort of an arrow pointing through space with a magnitude and a direction. And the difference, though, is that these vectors consist of thousands of dimensions. So they're sort of hard to understand with our human brains, but computers are really good at understanding these things and representing them. So once we have our source data embedded into our vector embedding format, we can then store all this data within our vector database. And here is where the power really begins, because now we can take a user's query. Well, it could be a natural language question, it could be an image, it could be a piece of audio. We would embed that the same way that we embedded all our original source data. And then we can do similarity searches on our vector database. And what this will do is return the most relevant matches or the most relevant vectors, and it will output that and return those as our query results. And then we can pass those to other pieces of our application, or just use those similar results immediately. So when we think about that actual similarity search portion of this, how does this work? And if we look at these examples here, just in a 2D plane, we could sort of represent it where the yellow dots are our vectors that we have stored in our vector database. And then the user sends in a query vector. And this query vector can then be compared to all of the surrounding vectors, and we can return the most similar ones depending on which similarity method we are using. So in KDB AI, we have several different options for how we can do these similarity searches. We can use algorithms like Euclidean distance, cosine similarity, or dot product. And depending on our use case, we may need to do a little testing to decide which one would be the best for our use case. But regardless of what we choose, the idea is we would be returning the most relevant vectors from our vector database to the query vector, and then returning that as an output to our query. So this is sort of the core of how a vector database works. And this is the similarity aspect, but there's also in KDB.ai the ability to do outlier search as well. So we could find anomalies and the least related vectors. So there's a couple different ways we can approach this. But with that, how can we take this search and take our vector database and then improve retrieval past just a general vector search? And there's several different capabilities that we have that can do this, but today we're going to be looking at hybrid search. And this is a method where we actually combine two different types of searches together to try to get the best results out. And if we break this down a little bit further, this is how it works. So number one, we have our dense vector search. And if you look at this diagram, the dense vector is sort of what you think about typically with semantic searches in vector databases, where you take your documentation, you run that through an embedding model to get your dense vectors, and then your dense vectors are stored in your vector database. And we can do similarity searches with that. But this sort of misses out on something, which is dense searches are good for understanding underlying semantic meaning, but they miss out on some of the domain-specific keywords that maybe they weren't trained on. So if you were searching for some specific keywords, and the dense vector may not capture that as well as you might want it to. So that's why we introduced the second kind of search, which is a sparse vector search. So a sparse vector is also a vector, sort of similar to a dense vector, but slightly different, and it really represents all of the keywords in our documentation. And it's able to represent the importance of those keywords by the number of times that they are basically within a document or within a specific chunk. So with this, we have the ability to capture the keywords within our documentation as well as the underlying meaning within our documentation. And then we can store both of these types of vectors within different columns within our vector database. And from here, we're able to actually do two different searches and then combine the results to have A, dense vector search results, and B, sparse vector search results, capturing semantic meaning as well as specific keywords. So with that, I will go ahead and pass it off to Michael, and he's going to deep dive into all the technical aspects of how the hybrid search works. So Michael, if you want to take it away.
Let's do it. Thanks, Ryan. Let's begin the deep dive into how dense vectors work. Now, imagine you have a document and you want the computer to understand its meaning and be able to compare its meaning with other documents. And the solution to that is a dense vector. Dense vectors are high-dimensional vectors that could reach thousands of dimensions, but most of these values are non-zero. And even if they are zero values, they are stored in memory. Now, what this allows us to do is we could capture very rich semantic meaning and relationships in a document. And after that, we can also capture relationships and very clearly compare different documents and see whether they are related. Now, this is done with powerful embedding models like sentence transformers, text embedding, small, clip, image bind. So we could create dense vectors for all kinds of data, including multimodal data. So we could create dense vectors for text, images, a mix of both, or pretty much any kind of data we can imagine. And then once we have these rich, semantically rich dense vectors, we can then compare them and use vector search similarity metrics like Euclidean distance, which is just how close they are to each other, cosine similarity, how close the angle is, or dot product, which is just the normalized multiplied value of these vectors. Now, depending on how you actually got these vectors, which embedding model did you use, for example, you might want to use a different similarity search. But the point is that even though these dense vectors capture rich semantic meaning, sometimes you want to capture keywords as well. And for that, we can move on to the sparse vectors. And sparse vectors have the advantage that they basically count how often your keywords happen, right? So again, we use a tokenizer. In this case, we use BERT tokenizer fast from Hugging Face, for example. And these tokenizers break text into smaller subsections. And then we could take account of how often each token happens and use that to enhance our search. Now, these vectors are also can range into thousands of values, but most of these values are just 0 elements, and we highlight the non-zero elements. So it takes much less memory to store, but we have the advantage of actually having a count of each token, right? So if you have some lexicographically rich data, like legal documents, where every single word is extremely important, then sparse vectors will be extremely useful for you to find what you're looking for. But the thing with sparse vectors is that they almost completely miss semantic meaning, because while we have a count of how often each token occurs, we're not really looking at where these tokens actually occur in space. And for that, there is another solution that combines sparse and dense vectors called hybrid search. Oh, but let's talk about sparse search a little bit more for a second. So it was developed in the 1970s for document retrieval, and until recently, this was basically how most search algorithms worked. Dense search only became much easier once vector databases became a thing recently, and embedding models became cheaper and more widespread. So what we do is with sparse search is we rank documents again based on relevance to a query, but this relevance considers term frequency, right? How often does this keyword or token actually happen? And how we actually implement this in KDB AI is we use an inverted index. So we take a token and basically just count how often it appears. And we identify every single document that has a given term. Now, how we actually count this is not extremely relevant. We use IDF, which is just an algorithm that we get used to calculate the score. But what's important here with KDB AI is once you insert new data for a sparse column, all the underlying BM25 statistics are updated. That just means your scores are always up to date. And most of our competitors, as far as I know, don't have this. Now, this is important because whenever you have new data coming in, you don't have to wait for the entire index to update. And it will be always correct no matter how much data you're putting in. Now, how does this happen in practice? Let's say you have an inbound query, which could be an image or a question that the user is asking. And when you're actually doing retrieval, which is you're fetching from the database, you first want to take this query and embed it. Now, you might be familiar with embedding models that you use for dense queries. Like there are all kinds of embedding models you could use. But in hybrid search, you actually use two embedding models. You use a large embedding model like a dense embedder, to get your dense query vector. And you also use BERT tokenizers to get your sparse query vector on demand. And then you use both of these in your search. And you could also put your hyperparameters on demand. Now, what happens when you have these two queries is we use a BM25 sparse search and a dense search and fetch the top K results. And then we use a algorithm called reciprocal rank fusion. And based on your alpha parameter, which decides how much importance you want to give to your dense and sparse vectors, you create a re-ranked output. So we are able to, in a way, get the best of both worlds. We are able to capture the semantic meaning that dense vectors can provide, while also looking at keywords, which for depending on your data might still be extremely important. So how does this happen in terms of our hybrid search schema? So our schema just looks like a regular schema for dense vectors, but what we do is we add another sparse column. So right now we have this dense column, which has our similarity metric, our number of dimensions. And we also have a sparse column, which is a similar dictionary, but now we also have this sparse index. And the sparse index has K and B values, which are hyperparameters that I don't want to dive too deep into. But once you define this, you'll be placing, when you insert data, you'll be inserting sparse values and dense values alongside your metadata. And this allows for a much stronger search when you're actually querying it at query time.
Yeah, that's great insight, Michael. Thank you. And just to add too, so when you are defining your columns, these are used when you're going to go ahead and create the table within KDB AI. You're going to create the actual vector database there. So you do define these sparse and dense columns, which will enable you to do vector hybrid search. But you also have the ability to define other columns as well, which might hold additional metadata. And it's always good in your use case if you can add metadata to do so, because you can use that later down the line to do additional filtering on your queries, which will also improve your search results. So I just wanted to add that in.
Excellent, Ryan. Yeah, metadata filtering is an extremely important way to further filter your search, because this filtering step happens before the actual sparse and dense search parts, which can greatly improve performance, especially when you have millions or even hundreds of millions of data points. All right, let's talk about the alpha parameter. Now, the alpha parameter defaults to 0.5, but as it moves closer to 0, this indicates that we're doing a pure sparse search. And closer to 1 means we're doing a purely dense vector search. Now, when we're doing a query, we could define this alpha parameter based at query time. So we don't have to define it when we're actually putting in the schema. And we could also dictate additional hyperparameters as well. Now, BM25 has hyperparameters called B and K, which we could tune at runtime. Now, B is just the document length's impact on relevance. So basically, whenever you have documents that are covering very specific topics, you should use a lower B. And when your documents cover many different topics, then a higher B is usually more effective. And K just means term saturation, which is, okay, like you have additional instances of a term coming over and over, and a K just defines how quickly does this term not increase the document's performance. So lower K just means faster term saturation. If you want to learn more about these hyperparameters, we explain them in our documentation. But yeah, in general, these B and K parameters aren't nearly as important as this alpha parameter. This alpha, if you're going to tune your results and try to figure out what is the step that you can take that has the largest effect, this alpha parameter will be much more important, because you really want to figure out, based on your specific data, what is more important for your search. Is it your keywords, or is it the semantic meaning of your documents?
All right. Well, thank you for taking us through the deep dive there, Michael. Really appreciate that. And now we'll take a step back and talk about what are some potential use cases that would be a good fit for hybrid search. So really, you could look through all these use cases, but what it comes down to is, if you have a use case where there's domain-specific terminology, that is likely going to be a good use case for hybrid search, because you're able to capture those keywords and weight the importance that they have with that alpha parameter on your vector search. So if we think about like a legal document search, for example, there's all sorts of specific legal phrases, legal citations, and dense search by itself is really not going to likely do well with this sort of terminology. So if we can tie in dense search alongside sparse search, that will help to solve this problem and increase the relevancy of your results. And another one I like to think of that's sort of similar to this would be like a medical use cases where you have complex medical terms. You could think of a use case with human resources and recruitment, doing resume matching, where you're looking for very specific skills on a resume, and a sparse search is going to be better at capturing those specific skills. And then you could also tie in the dense search to find maybe the general semantic meaning of the experiences that a candidate might have. Ideas like content recommendation systems, where you're matching user preferences and behaviors with relevant content. So maybe they have specific interests and preferences that they might have. You could sort of tailor that towards the sparse search. And then also just the general behavior that they have might be able to be captured better with a dense vector search, showing the more of the underlying semantic meaning. And then customer support, same sort of thing. You're looking to retrieve relevant information from a knowledge base and pass that on to a customer. The customer may ask questions that have very specific keywords in it. Therefore, sparse search may be a good option for you. And of course, combining that with dense search and tuning that alpha parameter to get the best results will likely yield the best retrieval. So these are just a few use cases, but if you sit down and think about it, you could expand these to many different use cases, because let's be honest, a lot of use cases have very domain specific keywords associated with them. So with that, I wanted to get into retrieval augmented generation a little bit and how this ties into RAG very well. And for those of you who aren't familiar, we'll do just a very fast overview here. And the idea of RAG is to introduce our own data to a large language model. And we would want to do that because large language models, they have knowledge cutoff. They aren't trained on all of your data. So they're not going to be able to answer questions about your data specifically unless we use RAG to introduce our data to the large language model. So to do this, what we can do is we can take our data, we can chunk it up into smaller pieces, and we chunk it up into smaller pieces so they're more manageable, they're more granular and specific, and hold specific topics, and that this way they'll easily fit into the large language model's context window. And after we chunk it up, we'll go ahead and do the run these through the embedding in the tokenizer. So you could think about, for each chunk, we're creating a sparse vector and a dense vector, and then storing these all in the K2B-AI vector database. So at this point, we have all of our data stored in this vector database, and we want to be able to retrieve relevant data and send that to the large language model. So if a user is going to send a prompt, we'll just take that prompt and we'll embed that and tokenize it in the same way that we did our previous data. And then with our new sparse and dense vector query vectors, we can take this and run a hybrid search against our vector database. And therefore, we can retrieve the most relevant data from our vector database from that hybrid search, and send that relevant data as well as the user's prompt to the large language model. And now the large language model will be able to actually answer questions about this data that it hasn't seen before. And when we use the hybrid search here, it's no longer just capturing the semantic meaning, but you're bringing in the keyword aspect of it as well. So the idea is just let's increase the relevancy of these results as much as possible. And for certain use cases, hybrid search is going to be a really good way to do that. All right, so that is the slides for today, but now let's go ahead and take a look at our coding demo. And we're just going to run through this and show how a very simple example, but an example that shows how you can actually implement this in practice. So I've done a few preliminary steps already just to save us some time, but we need to go ahead and do our initial installs, make sure we have everything that we need. And I've already done this step. But the next thing we're going to do is we're going to download our data. So what's going to happen here is that we just downloaded a speech from the Federal Reserve that talks about inflation. And I believe this is from August of 2023. So if you're interested in this notebook and learning more about this data set, go to our GitHub samples page. We have this as well as many other samples available for you there, where you can easily get started and try some of these out.
I just want to add that that's also on our Learning Hub as well. So just KidBAI Learning Hub, you can just find the sample easily with that.
Perfect. Thanks, Neil. So we downloaded our data. We have our inflation speech here. We can take a little look at it. It's a speech that goes into it, all the things going on with the country and inflation. So what we need to do now is we will go ahead and import everything that we need, which I did already run this step. But now we're going to go ahead and load that data. So we downloaded it. Now we're going to load the data so we have access to it. And the next thing we're going to do is we're going to chunk it up. So what we're doing here is we're taking our data and we're just splitting it up into smaller pieces. And all these chunks then will be used to be stored within the vector database. So now we have our data, it's chunked up. And what we're going to do next is just create a blank data frame. So this is where we will go ahead and process, we will create our embeddings, both sparse and dense embeddings, as well as our chunk, and we'll just store all this in here. And then later on, once we have filled this up with all this information, we will use this to actually ingest data into the KDB.AI vector database. So now the next step is going to be, let's create our tokenizer model and our embedding model. So the tokenizer model, the BERT tokenizer here, this is going to be used to create our sparse vectors. And then we're going to use a sentence transformer model that will be used to create our dense vectors. So with these two models, we'll be able to create both of those vectors. And now let's actually create them. So this step is going through, it's creating our dense vectors here, creating our sparse vectors here, and then we're just appending all this information into that empty data frame that we just defined above. So let's give this a run. It should take a few seconds to do. All right, and then we print out at the end. So this is a sample of what our data frame now looks like. So we have our chunk, which is the actual raw text. We have our dense vector, which was created from our chunk. And then we have our sparse vector, which was also created from our chunk. So now we have all the information that we need to run a hybrid search. So the next thing we'll do is define our KDB.AI session, which I have already done. We're already connected, but when you do this, all you'll need to do is sign up for your KDB.AI account, and then you'll get your endpoint as well as API keys there. And it's really easy to get started. You can go ahead and just plug these in and connect to the session. And at this point, we are connected to the KDB.AI session. The other option is to use the server mode too. So if you wanted to host the server yourself, you're more than welcome to do that. So now we need to create that schema. And just like Michael talked about earlier, That schema is going to contain a couple of metadata fields that will have the ID as well as the raw chunk, but then we have our fields for sparse and dense vectors. So once we define that, we're going to go ahead and run this code. So what's going to happen here is we're checking to make sure we don't already have a table that's named inflation1. And then we're going to actually go ahead and create a new table called inflation1 with the schema that we just defined above. So at this point, a table or a vector database is being created, and it's being created with this schema. So we can take a look and say, okay, we have an empty vector database now. And we have all the columns that we defined in the schema right there. So let's go ahead and insert some data. So we just inserted the data, all those chunks and all the embeddings, and now we can take another look and see that indeed our data was inserted. We can see all our columns and chunks, the sparse, the dense vectors. So I think we are good to go to try out some sparse, dense, and hybrid queries. So what we're going to do is let's take a look at this idea of the 12-month basis. So I'm someone coming in. I want to get information about the 12-month basis. So what we'll do here is actually take this query, which would be the user query. We will embed that query to get our dense query. We will run that query through our tokenizer to get our sparse query. So now we have both our dense query vectors and sparse query vectors from the original natural language query. And we will just do a little setup here. And then let's run a dense search. So now we can actually run a dense search using that dense query vector that we just created. So here we're just going to return the top 5 results, and we're just going to return the ID in the chunk just for ease of reading. But this is what it returns. And looking back at the query, we see 12-month basis here, and we're looking through this. And the results, they're probably relevant in some degree to the 12-month query, but really, I don't even see 12-month query, 12-month basis in here at all. So, not that great. But what if we try a sparse search? What happens? With the sparse search, we start to see the 12-month basis actually popping up. And it's actually popping up quite commonly here. So this starts to do the comparison, right, between the dense vector and the sparse vector. And we can see that in cases where you have some specific words that are mentioned, it's likely that the sparse search is going to give better results that are more focused on the actual keywords that you're interested in. So now that we see like the benefit of tying the two types of searches together, we can actually combine them within a hybrid search. So this takes both our dense vectors and our sparse vectors and does a search that combines both of them. Now, when we do this without setting an alpha parameter, we're just splitting it right down the middle. So that alpha parameter is default set at 0.5. So if you look at these results, you see sort of a mix and match. Like you get some dense result here, you see the sparse result here, and so you're basically getting a 50-50 mix of each of them. But in certain use cases like this one, it's probably likely we want to weight our search a little bit more to the sparse bias because we're really interested in this 12-month basis. We still want to understand some of what the dense search is going to give back, but really we want the 12-month basis. So in this case, we can actually set that alpha parameter at as we're running this query and weight that towards our sparse search. And to do that, we just mark this a little bit closer to 0. And in a case, we maybe have a use case where we're more interested in the dense results. We just do the opposite, and we just put alpha a little bit closer to 1, and then you get a higher weight towards our dense results. So that's how hybrid search works. And the last little bit I want to talk about is this additional flexibility for hyperparameter tuning to be in the K. So You can do this at runtime, and a lot of the other vector databases out there do not have this capability. If they offer hybrid search, they likely do not have this capability for doing the tuning of the underlying BM25 parameters, especially at runtime. So we make it really easy just to set these parameters, and depending on your use case, depending on your documentation, setting these parameters could increase the relevancy of your results. So it's as simple as just setting it right in your query here. You can run this, and it'll, depending on your use case, it could improve results. And then you just have to do some testing to find out, what would be the best combination of the two. And then, as always, at the end of our work, we like to drop the table just to save resources. So that is the coding demo for the day, and happy to open the floor if there's any questions.
Yeah, we don't have any questions that have come in yet, but there's still time. If anyone has questions, be sure to just go ahead and put them in the chat. This is an excellent demo. I think we had a lot of folks asking in previous sessions on, I think, our chunking best practices session, like how come I'm, querying my vector database and I'm not getting specific terms back, and I'm not getting and that's really because of the dense embeddings and it going off semantic meaning. And so I think what you and Michael outlined, was a really great way to blend the two approaches and improve that accuracy. It makes it much more applicable in real world scenarios, and it works very elegantly. I really like this, and I think it's an excellent notebook that others should feel encouraged to try out. Also, lots of other notebooks in our Learning Hub, and lots of other videos on our YouTube. So if you are interested in things like metadata filtering and chunking and RAG, I would check those out as well. But yeah, not seeing any questions today. Oh, actually, there are 4 questions. I wasn't looking at them. Oh, okay. So I think you've already answered these questions in the session. So I'm a little late to see them. I wasn't looking at the right screen in our broadcast UI, but looks like you've already answered these questions. And if there's any other questions folks have after the session, just ask us on LinkedIn. You can always comment on this thread, or feel free to message us directly. Or best way to really get a hold of experts with vector databases is join that Slack channel as well. So I just want to throw that in. Before we close out, I want to remind everyone that this session is going to be on YouTube in just a couple moments after we end the live stream. It will automatically go onto YouTube, so you can watch it there, share it with whoever you like. And I wanted to also mention that we have that Slack channel. So when you sign up for KWAI, you can get access to that. Lastly, we're going to be doing a session on, I believe, April 17th in 2 weeks on introducing temporal similarity search. We'll be joined by Michael and Ryan again. This is something truly innovative that we're doing at KX. Haven't seen this by anyone else out there, but when KX really specializes in temporal data, time series data, and we're now bringing in that structured and unstructured approaches to improve your anomaly detection, your forecasting, your patterns, your pattern matching. So it's going to be a really cool session. You want to see something unique and new in vector databases, highly recommend you join. And with that, I guess we can close out the session. If Ryan and Michael, you had anything else to add, feel free. Okay. Well, thank you all for joining today, and hopefully we see you in 2 weeks. And have a great rest of your day. We will catch you next time. Thanks.
Thank you. Thanks for joining.